A celestial object is defying the laws of physics as it is apparently rushing towards our planet. NASA and European agencies are on a bit of a high alert, and the United Nations International Asteroid Warning Network is also very closely watching. And our next story gets you more details about the 3I Atlas.
We've been tracking 3I Atlas for months now, and on December 19th, it finally made its closest approach to Earth, which means we can answer the question, where is this thing? And the short answer is it's leaving and it's not coming back. And scientists just released new observations from the flyby, and honestly, it just keeps getting weirder. This thing is glowing in a way that it's not supposed to be glowing, and it's still got a tail pointing in the wrong direction, which doesn't make any sense. And now there's a very real possibility that we're going to watch this object disappear into the void without ever figuring out what it actually is, unless scientists can make a decision in the next few weeks. So let's start with where this thing is right now and why that's a problem. Where it is right now. Right now, 3I Atlas is in the constellation Leo, sitting just below the star Regulus, and it's moving away from us at about 67 kilometers per second, which is 148,600 miles per hour, and getting farther every single second. On December 19th, when it made its closest approach to Earth, it was 185 million kilometers away, which sounds far, but that's actually closer than Mars gets to us most of the time, and it was the best view we were ever going to get of this thing. And here's the problem. Even at closest approach 3I Atlas was magnitude 8, which means you can't see it with your naked eye, and you can barely see it with a decent backyard telescope, and now that it's moving away, it's getting dimmer every day. Right now, it's sitting at magnitude 13, which requires serious equipment to even locate, and by the end of January, it'll be magnitude 15 and effectively invisible to most amateur astronomers. And by March, when it flies past Jupiter, it'll be magnitude 17, which is so dim that only the world's most powerful telescopes will be able to track it at all. The rate at which it's fading tells us something important about what's happening to the object itself. And as 3I Atlas moves farther from the Sun, it's cooling down, and the sublimation process that creates the coma is slowing down and eventually stopping altogether. Right now, the coma is still visible, extending about 500,000 kilometers from the nucleus, but it's shrinking every day. And by the time the object reaches Jupiter in March, that bright, fuzzy halo will be mostly gone, and what's left will be a small, dark nucleus surrounded by a thin shell of residual gas. And amateur astronomers who've been following 3I Atlas since summer can actually see this happening in real time, and the astrophotography community has been posting images showing the coma getting smaller and dimmer week by week. Back in October, when the object was approaching perihelion, it was this bright glowing ball with a distinct tail, and now it looks more like a faint smudge, and in another month it'll be barely distinguishable from a distant galaxy. So we're watching this thing fade in real time, and once it drops below magnitude 20, sometime in mid-2026, we lose it completely, and it goes back to being just another invisible speck drifting through the void. And that would be fine if we had already figured out what this thing is, but we haven't. And that's what makes this moment so critical, because we're running out of time to get answers. Now, let me show you what we learned during the December flyby and why it's got scientists scrambling. So, between December the 3rd and December 18th, multiple X-ray telescopes were pointed at 3I Atlas. And this is huge, because no interstellar object has ever been observed in X-rays before. We got X-ray observations of 1I Oumuamua after it was already leaving, and we got some from 2I Borisov, but they didn't show anything interesting, and most comets from our own solar system don't emit X-rays at all unless they're extremely close to the Sun. But 3I Atlas is different, and this is what wasn't supposed to be possible. The X-ray observations showed a distinct red glow extending about 300,000 kilometers from the nucleus, and that's almost as wide as the distance between the Earth and the Moon, and the glow is being caused by something called charge exchange, which happens when solar wind particles hit neutral atoms in the coma and strip away electrons. And when those electrons recombine with other atoms, they release energy in the form of X-rays. Now, that process is normal for comets that are very close to the Sun, but 3I Atlas was still 1.4. Astronomical units away from the Sun during these observations, which is about the same distance as Mars, and at that range, the solar wind should be too weak to create this much X-ray emission. So either the coma of 3I Atlas is way more dense than we thought, or there's some other process going on that we don't understand, and both of those options are weird. To put this in perspective, the brightest X-ray comet ever observed from our own solar system was Hyakutake back in 1996, and it only lit up in X-rays when it got within 0.1 astronomical units of the Sun, which is inside Mercury's orbit where the solar wind is incredibly intense. But 3I Atlas is producing comparable X-ray brightness at 14 times that distance, which suggests the coma has an unusually high concentration of carbon monoxide and carbon dioxide, and other molecules that are particularly good at charge exchange. And we know from earlier spectroscopic observations that 3I Atlas does have a CO2-dominated coma with an 8:1 ratio compared to water, which is basically the inverse of a normal comet. So that could explain the X-ray brightness, except it doesn't fully explain why the emission is so red, and the color of X-rays tells us about the energy levels of the electrons that are being recombined, and red X-rays are lower energy, which means the charge exchange is happening with heavier atoms like oxygen or nitrogen rather than lighter ones like hydrogen. But if the coma is mostly CO2, then we should be seeing charge exchange primarily with oxygen atoms, which would produce red X-rays, so maybe this does make sense. Except there's a paper from early December that analyzed the X-ray spectrum in detail and found emission lines that don't match pure CO2 charge exchange, and instead suggest there's a significant amount of nitrogen compounds in the coma which we haven't detected in the visible light spectrum. So either our visible light observations are missing something, or the X-ray observations are picking up a component of the coma that only exists in a thin outer shell where charge exchange happens. And then there's the anti-tail situation, and remember how I said the tail is pointing in the wrong direction? Well, it's still doing that. Most comets develop a tail that points away from the Sun because the solar wind blows all the gas and dust in that direction. But 3I Atlas has been sporting this secondary tail that points toward the Sun, and it showed up back in August when the object was still way out beyond Mars, and everyone assumed it would disappear as the comet got closer to the Sun, and the solar wind got stronger, but it didn't. During the December observations, the anti-tail was still there, and it had actually gotten longer, extending about 1 million kilometers in the direction of the Sun, while the normal tail extended about 3 million kilometers in the opposite direction. And there are only a few ways to explain this, and none of them are completely satisfying. Avi Loeb has published 3 separate papers trying to explain the anti-tail, and his best theory so far involves the rotation of the nucleus combined with asymmetric outgassing, where jets of gas shoot out from specific spots on the surface as the object spins, and if those jets are timed just right, relative to the Sun's position, they could create the illusion of a tail pointing toward the Sun, even though it's technically just gas being pushed sideways. But the math only works if the nucleus is rotating at a very specific rate and has a very specific shape, and is made of very specific materials, and that's a lot of coincidences stacking up. The other explanation that people don't want to talk about is that maybe the anti-tail isn't a tail at all, and it's actually a plume of material being actively expelled in the direction of the Sun, which would require some kind of internal energy source, and that starts sounding less like a comet and more like something with a propulsion system. And before you write that off as crazy, remember that we still don't have a good natural explanation why 1I Oumuamua accelerated as it left the solar system, and 3I Atlas is doing things that are just as strange. Now, let me tell you what happens next and why scientists need to make a decision fast. So, 3I Atlas is leaving the inner solar system, and by early January, it'll be past Mars orbit, and by February, it'll be approaching the asteroid belt, and then on March 16th, 2026, it's going to fly within 53.6 million kilometers of Jupiter. And that sounds far, but it's actually pretty close in space terms. And more importantly, we have a spacecraft already at Jupiter that could potentially intercept this thing. The spacecraft is called Juno, and it's been orbiting Jupiter since 2016, studying the planet's atmosphere and magnetic field, and its mission was supposed to end back in September 2025, but NASA extended it because the probe is still functioning perfectly and there's still good science to do. But here's the thing, there's a paper published in September 2025 by Avi Loeb and 2 other researchers showing that Juno could be redirected to intercept 3I Atlas and get within 27 million kilometers with only minimal fuel expenditure, The paper lays out the exact trajectory calculations, and the optimal burn would have been on September 9, 2025, requiring about 110 kilograms of propellant, which is only 5.4% of Juno's initial fuel mass. That window passed, and NASA didn't take it, but the paper also shows there are backup trajectories that could still work. Even now, they just require more fuel and result in a more distant flyby, but it's still theoretically possible. And this is the decision scientists need to make in the next few weeks. Do they redirect Juno to chase down 3I Atlas, or do they let this opportunity pass? Because if Juno could get close enough, it would be the first spacecraft ever to observe an interstellar object up close, and the data we could collect would be incredible. We could measure the object's exact size and shape and composition. We could analyze the coma with instruments that are far more sensitive than any telescope on Earth. We could look for magnetic fields and charged particles and any other signatures that might tell us what this thing really is. Juno has a visible light camera called Juno Cam that's been taking spectacular images of Jupiter's clouds, and from 27 million kilometers, that camera could potentially resolve features on 3I Atlas down to a few kilometers in size. Not enough to see surface details, but enough to determine if it's elongated like 1I Oumuamua or roughly spherical, and enough to see if there are distinct bright and dark regions suggesting compositional differences, and enough to count how many pieces it's made of if it's fragmenting. The spacecraft also has a microwave radiometer that can measure thermal emission from the nucleus and tell us about subsurface temperature, and the ultraviolet spectrograph can identify specific minerals and ices on the surface and analyze the composition of gases in the coma with much higher sensitivity than Earth-based UV telescopes. And Juno's magnetometer could search for magnetic fields which would tell us about the object's internal structure and whether it has a metallic core, and the energetic particle detector could look for charged particles being released, which might indicate active venting or even electrical activity. And here's something that doesn't get talked about enough. We could measure the mass. By tracking how Juno's trajectory gets perturbed by 3I Atlas's gravity during the flyby, even from tens of millions of kilometers away, you can calculate the gravitational pull and therefore the mass of the object. Combined with size estimates from imaging, this gives you density, and density is one of the most important clues to composition. Is it a loosely packed rubble pile with density less than water? Is it solid ice with density around 0.9 grams per cubic centimeter? Is it rock with density over 2? Is it metal with density over 7? We absolutely cannot get this information from telescopes. But there are problems with this plan, and the biggest one is that Juno's main engine broke in 2016, and since then, all orbital maneuvers have been done using tiny reaction control thrusters that were never designed for this kind of velocity change. The paper assumes you could use those thrusters to pull off the intercept, but it would burn through most of Juno's remaining fuel, and there's no guarantee the spacecraft would have enough left over to maintain its Jupiter orbit afterward. So you're essentially sacrificing Juno's extended Jupiter mission to chase an object that might turn out to be just a normal comet. And here's the political reality. NASA is facing massive budget cuts right now, and the Trump administration has been slashing funding across federal agencies, and in that environment, proposing to end a successful mission early to gamble on an interstellar intercept is not an easy sell. Congresswoman Anna Paulina Luna actually sent a letter to NASA in July 2025, urging them to study this possibility, and NASA never publicly responded, and the optimal September window came and went without action. And this gets to a deeper problem with how NASA makes decisions in the current political climate, and the agency has become extremely risk-averse because every failure gets amplified by politicians looking for reasons to cut budgets, and every cancelled mission becomes ammunition for the argument that space exploration is a waste of money. So even though the AV Loeb paper shows that a Juno intercept is technically feasible and scientifically valuable, the institutional calculus probably says it's safer to keep doing the Jupiter science that's already approved and funded rather than pivot to something new that might fail. There's also the issue of timing, and the decision to redirect Juno would need to be made soon, like within the next month or two, to optimize the trajectory, and that means getting approval from NASA leadership and from the relevant congressional committees and from the Office of Management and Budget, and all of that takes time that we don't have. The optimal window was September 9th, and we're already 3 months past that, and every day that passes makes the intercept more difficult and more expensive in terms of fuel. And then there's the fact that Juno's main engine has been broken since 2016, which means any trajectory change has to be done using the reaction control thrusters, and those weren't designed for this kind of maneuver. The paper assumes it's possible, but there's uncertainty about whether the thrusters can maintain stable thrust for the extended burn time required, and whether the spacecraft's orientation control system can keep everything pointed in the right direction while the thrusters are firing. If something goes wrong during the burn, Juno could end up in an uncontrolled spin, or worse, could burn through all its fuel without achieving the right trajectory, and then it's game over for both the intercept and the Jupiter mission. So the most likely outcome is that Juno will stay at Jupiter and observe 3I Atlas from a distance of 54 million kilometers in March 2026, which is better than nothing but nowhere near as good as a close flyby. And after that, 3I Atlas will continue moving away from the Sun, and by late 2026 it'll be beyond Neptune's orbit, and by 2027 it'll be so far out that even our best telescopes will lose track of it entirely. And then it's gone forever, and we're left with all these unanswered questions, and that's what makes this so frustrating, because we had a chance to actually study an interstellar object up close, with a spacecraft that was already in position, and we're probably not going to take it. We'll watch 3I Atlas fade into the background noise of deep space, carrying all its secrets with it. And maybe in another decade or two, we'll spot another interstellar visitor, and maybe that time we'll be better prepared, but right now, in this moment, we're letting this one slip away. And that's where 3I Atlas is now. It's in Leo, moving away at 67 kilometers per second, and getting dimmer every day, and carrying all its mysteries with it back into the void. We got our closest look on December 19th, and what we learned only made things weirder. And now we have a narrow window to decide if we want to chase it down or let it go and watch it disappear. And the clock is ticking, and every second that passes makes the decision harder and the opportunity smaller, until one day soon there won't be a decision left to make because the window will have closed and 3I Atlas will be gone. If you enjoyed this video, please like and share for more 3I Atlas updates. Thanks for watching.